Alright, I'm going to do a lesson on an application of exponential base E, the E function. And again, the application is similar to the types that we've done before earlier in previous sections. The first example is we're going to optimize revenue. Now the difference between this and the previous types is our revenue function was a polynomial. Our price demand was linear. In this case, alright, the price, which is in dollars, the quantity demand is again some type of item, but this is our price demand and it's an exponential. Alright, so that's the new part. It's over a closed domain, so since it's a closed domain, I'll use the extreme value theorem when I go to solve. Alright, so the first thing we're going to find is the revenue function. So revenue, same as before, is price times quantity. This time though, price is not linear. The price function is the 250e to that negative 0.025x times another x. Just like before, again, the new part is that it's the exponential. Now I am going to rewrite this. Instead of leaving it x on the outside here, I'm going to move it into the 250. It just makes finding the derivative easier. So I'm just rearranging it, 250x times the e term. Again, I'm allowed to do that because it's multiplication, right? I can rearrange multiplication. 2 times 3 is the same as 3 times 2. Alright, so here is the revenue function that I'm going to optimize. Alright, so part B is we want to maximize it. Alright, well, it's the closed domain case because I've 0 and 800 brackets means they're included. And so we use the extreme value theorem, which means I need to find any critical values on the given domain. Alright, again, I only want those between 0 and 800. Alright, so find my derivative and solve for my critical values. Alright, my derivative is going to require me to use the product rule. There's two functions. There's the 250x, and then there's the e function. So product. And then when I take the derivative of the e, because it's got something up there with the x, I'm going to have to use my chain rule. Alright, so first, 250x times the derivative of the second, which is my chain rule on my e, which is write my e function down without doing anything to it. And then separately, separated by multiplication, the derivative of the inside, which is just that number, negative 0.0025. Alright, so that's the first. Derivative of the second plus the second, which is the e term, times the derivative of the first function. The first function is 250x, and so the derivative of that is 250. Right, because the derivative of x is 1. 250 is a constant that comes along. Constant multiplier. Alright, now I'm going to simplify by factoring because I know I'm going to solve for the 0, so I'm finding the critical value. So I'm going to factor out two things. First of all, I can pull out the 250. There's a 250 in each term. And then the e term. Right? And there's always an e term when I take a derivative using the product rule. Alright, what's left over? Well, the 250 is gone, but I still have an x and that negative number. So in the first term, I've got the negative 0.025 times x. In the second term, I pulled everything out. Remember, factoring means I'm dividing it out, so when I divide by the same thing, I'm still left with a 1 inside. Right, and that's the function I'm going to set it equal to 0. Right. The critical values are where my derivative equals 0 or doesn't exist. Well, this derivative exists everywhere. The polynomial part's the only part I can have 0. Remember, the e part is never 0. And so that's the only piece that can give me out the 0, the negative 0.25 x plus 1, and that's what I'm going to solve. And so I'm going to move my x over because I don't like negatives. I tend to lose them, so I'm going to leave my 1 there. I'm going to add the 0.025x. When it gets moved over the other side, I'm adding it so it becomes a positive, and then I divide by the 0.025, both sides. And that's going to leave me 400. Alright, so my critical value, that's my critical. It lands in my domain, so I'll keep it. And so remember, the test, because it's the closed case, right, is to input my endpoints and my critical values back into the original. So we're going back up here to the e function. So I'm going to take the revenue function. I'm going to take my 400, I'm going to plug it in. I'm going to take my endpoint 0 and plug it in. And I'm going to take my endpoint 800 and plug it in. So remember, Those are going back into the original revenue. I should get a max and a min. Again, I'm only interested in the max. So when I plug 400 in, I get 36,787 and 94 cents and change. 0 just gives me out 0. And when I plug 800 in, I get $27,067.05 and change. Alright, so this is the biggest one. That's my max. 0 is my minimum, because again, remember, extreme value theorems guarantees both a max and a min. And it should make sense if I don't sell any. I'm not going to generate any revenue, and that's going to be my minimum. Alright, my maximum is when I sell 400. Alright, so again, the answer to part B is when they sell 400 items, they maximize revenue at $36,787.94. Alright, and bear with my handwriting on this. Again, it's on a tablet, so it's a little messy. Alright, the last part is, well, what's going to make it all happen, right? I need to know what price to set my item at so that the demand reached will be 400, because when the demand reaches 400, I optimize. And so we want to find the price of the item. Well, that's the original equation they gave us, and you want to plug in your 400. So you're going to take the original price equation, that 250e to that negative, and multiply by our 400. And since it's a price, I'm going to round to the penny. Alright, so the price comes out $91.97. And so if we set the price at 90, whatever our item is, we set it to $91.97. The demand should be 400. When the demand is 400, I maximize. And so again, it makes the magic happen. Alright, the second one I'm going to look at, just because I'm practicing using these, is I'm going to look at the marginal cost function. Alright, so the marginal cost, remember, is the derivative of the cost. So in this case, it's just finding the derivative of this function. They didn't even ask you to use the marginal cost, although you should know how to do that and look at the previous notes for those kind of types. This is just practicing finding my derivative. And so I am going to have to use the product rule and the chain rule. Product because it's the e to the x times the natural log of 2x. And the chain because it's the natural log of 2x. Alright, so the first is e to the x. Then it's times the derivative of the natural log, which is 1 over what's inside. So 1 over 2x, but I'm not done. Times the derivative of inside, so times 2. Right, the derivative of 2x is 2. Alright, so there's the first, derivative of the second, plus the second, which is just the natural log of 2x, times the derivative of the first, so times just e to the x. Again, it didn't ask you to simplify, but I'm going to, because it's just a good practice to do that. And so I'm going to pull the e to the x out. I'm going to reduce, right, this 2 and 2 reduces to 1 over x, and then I'm left with just the natural log in the second term, and so my marginal cost function is e to the x times 1 over x plus the natural log 2. If I used it, it would tell me how much more, approximately, or it's an estimate, additional cost it would give me if I produced one more item.